another example of a trigonometric substitution, and one of my favorite examples, because if you can identify a really slick way to evaluate this without using a trig substitution, then this problem can take a matter of seconds. But I'm going to illustrate it first how to evaluate with a trig substitution, and then I'll show you another way that if you look at it the right way, not using any sort of substitution or even integration technique, that you can evaluate this integral really quickly. So we're going to go back and we're going to notice that this is of the form a square minus x square. And in this case, a is going to be equal to 2. Okay, so that's easy enough. And so our trigonometric substitution that we're going to use is x is going to be equal to 2 sine theta. All right, so remember it's a sine theta whenever we have constant minus x squared. And from here, what we're going to do is we're going to divide by 2 sine theta. We're going to construct our triangle. And so nothing different so far. Right? We know that sine is going to be opposite over hypotenuse. So we have a hypotenuse of 2 and the opposite of x. And of course, we could go through and use our Pythagorean theorem, or we could just recognize that this is going to be the rational sort or the radical sort of expression that we have inside of our integrand. And that's not always the case, but a large majority of the time it is. Now, we still need a couple more things for this particular problem before we can actually go through and solve. One thing we always need is we need dx. All right, so in this case, the derivative of 2 sine theta is going to be 2 cos theta d theta, which is easy. And one last thing that we need for this particular problem is we are going to solve for theta. All right, and so to solve for theta, we're going to take the arc sine. So arc sine of x over 2 is equal to theta. All right, now you might be questioning why we need to do it in this problem and we haven't done it in any of the other problems. It's just at the end, when we go back to substitute, we're going to have a lonely theta in our answer. You can do this every single time that you perform a trigonometric substitution evaluation. However, you don't always use this theta. All right, so let's get down to the substitution. And remember, this is a definite integral. So at the end, we're going to have to do a little bit of substitution in here. This is actually pretty easy to substitute for. We substitute for x. That's going to be our 2 sine of theta. And then dx, we have a 2 cos theta d theta. So our integral now becomes integral. We're going to use our dummy variables a to b, square root of 4 minus the quantity of 2 sine theta square. And then we have this 2 cos theta d theta for dx. All right, so far not looking too bad. Now let's just simplify this radical expression. And you're probably getting the hang of this now. We've seen it twice already. So 4 minus 4 sine square theta, which is going to be equal to, if we factor 4 out, 1 minus cos or sine squared of theta. Getting ahead of myself. This is going to be now Pythagorean identity, cos square theta. And so ultimately we wind up with 2 cos of theta. All right, so nice and easy so far. Now our integral is going to become the integral of, instead of this, we're going to have 2 cos theta. So we have 2 cos of theta, and then we have another 2 cos theta, and then a d theta. Otherwise known as 4 integrals of cos square theta d theta. All right. Now, this is where it gets a little bit tricky because once again, we have to go back to our previous section and remember those rules of trigonometric integrals. One of the rules that we might remember is that we have a power reducing formula, and cos squared of theta can be written, and this should be from A to B, by the way, for each of these. I just neglected to bring down the limits of integration. That's going to be 1/2 plus 1/2 cos 2 theta d theta. All right, so that's our power reducing formula. All right, it's for our cos square. Get used to it. We use it a lot in the course, even towards the end when we start looking at polar and parametric curves. All right, now we're going to integrate each term with respect to theta. Okay, keep in mind that we have a 4 out there. So now we have 4 quantity antiderivative of 1/2 with respect to theta is going to be 1/2 theta. Antiderivative of cosine is sine, but if we were using the chain rule for derivatives, we multiply by 2. Now we're going to divide by 2. So this is going to be 1/2 times 1/2 sine of 2 theta from A to B. Now I'm going to clean this up a little bit by distributing the 4. This is going to turn into 2 theta. So 4.5 is going to cancel out, and then we have 4 half. So this is going to be sine of 2 theta from A to B. All right. Now, here's one of the sneakiest parts of the problem, back substituting. And this is where a lot of students make mistakes in this case. Okay, so they see a sine of 2 theta. And so what they're going to do is they're going to go back up and they're going to say to themselves, okay, well, sine of theta is opposite over hypotenuse. And because it's 2 theta, it's going to be 2 times the opposite of the opposite over hypotenuse. Okay, that is not correct. Okay, what we're going to do instead is we're going to use one more trigonometric identity because we want to make sure that this is not 2 theta, because the only thing that we have in our triangle is just theta. We don't have 2 theta. And we can't just double the angle, okay, because that wouldn't necessarily be trigonometrically correct. All right, so what we are going to do is we are going to use a double angle formula. Right? And you might remember from trigonometry that sine of 2 theta is equal, that's a theta in English there, sorry about that. Again, difficult to write on the screen, is 2 sine theta cos theta. All right, so remember this formula. This is one that you probably want to write down somewhere on your note card, along with your power reducing formulas. All right, so one last trig formula, and then we can do back substitution. We're going to have 2 theta plus, instead of sine 2 theta, 2 sine theta cos theta from A to B. All right, now let's back substitute. At the very beginning of the problem, remember we said arc sine of x over 2 is equal to theta. All right, so we go back down here, and we're going to end up with 2 arc sine of x over 2. All right, so that's our theta. And sine, so remember, sine is going to be your opposite over hypotenuse, and cosine is adjacent over hypotenuse. All right, so if we do that, let's go back up. Our opposite is x, our adjacent is 4 minus x squared, and then our hypotenuse is 2. All right, so if we plug those back in, opposite x, hypotenuse 2, adjacent square root 4 minus x squared divided by 2. And now we can back substitute the original limits of integration. Okay, so again, opposite is x, hypotenuse is 2, adjacent 4 minus x squared, hypotenuse 2. All right, now of course, before we substitute, we can just do this and get rid of those. And so if we really wanted to simplify it, that's fine. All right, so now we're going to substitute 2, and now we're going to substitute 0. Okay, so don't get too weirded out about this. Okay, so, the good news is these are actually pretty easy to evaluate once we get down to the end. All right, so we're going to have 2 arc sine of 2 over 2 plus, so we have 2 times the square root of 4 minus 2 squared divided by 2. Right? So that's when we substituted 2 back in, and now we're going to substitute 0 back in. So minus the quantity of 2 arc sine of 0 over 2, and then plus 0 times the square root of 4 minus 0 squared divided by 2. All right, so let's play good news, bad news. Bad news is we have arc sine. Good news is we have a lot of stuff that's going to cancel out. Notice right here, we have 0 times square root of 4 over 2. Doesn't matter with square root of 4 over 2, it goes away. Right here, we have 4 minus 2 squared. Well, that becomes square root of 4 minus 4, which is 0. So that cancels this out, right? We have arc sine of 0. All right, so basically, remember the sine is the y coordinate, and what we're asking is the sine of what is equal to 0, because 0 over 2 just becomes 0, and that answer is going to be 0. All right, so that goes away too. And if you don't believe me, just use your calculator, put it in radian mode, and check it when you're done. So realistically, this just turns into 2 arc sine of 1. And so ultimately, we're left with the question, the sine of what is going to be equal to 1? And we know that the only time the y coordinate on the unit circle is equal to 1 is right here at the point 0, 1, and that's at the angle pi halves. So we have 2 times pi halves, which ultimately is just going to turn into pi for us. All right, so answer, pi. All right, now you may or may not remember, because it seems like it might have been like 15 minutes ago, but remember at the beginning of the problem, I said that if we keenly note a way to try to evaluate this integral, and remember the original integral was 0 to 2 square root 4 minus x squared dx, that we wouldn't have had to use a trig substitution. In fact, we wouldn't have had to use any analytic method, right? One of the methods that's powerful on occasion is geometry, okay? Now, looking at this graph, this is just going to be a semicircle, okay? So if we were to graph this, this is just going to be a semicircle of radius 2, okay? So think about this. The domain for this is from -2 to +2, okay? If you just look at the function, it's pretty easy to see that. But we're only looking for when x is between 0 to 2. So we're really looking at this area right here. Okay, so this is when x is 0, and this is when x is 2. We know that the formula for the area of a circle is pi r squared. But we don't want the whole circle, we just want a quarter of the circle. So a quarter of the area is a quarter pi r squared. We know that the radius of this circle is 2. Okay, so no matter what, where we draw, the radius of this circle is going to be 2. And so the area for this is going to be 1/4 pi times 2 squared, which is just pi. All right, so now again, geometry is one of those types of evaluations where we can just sketch the curve and evaluate it. It really doesn't happen too nicely often. All right, there's many, many more definite integrals that cannot be evaluated using just basic geometry than just using our fundamental theorem of calculus. Okay, so this way was really taxing. This way was pretty slick, but we had to be able to recognize it. Okay. All right, so just illustrating that there are occasions where geometry can be helpful. All right, so we do have a few more examples of being able to evaluate these sorts of trigonometric substitution integrals, and we're going to look at those in subsequent videos.